So, good afternoon, students. Welcome to class 2 of quantitative methods in economics 2, which is being facilitated by me, the part which is being facilitated by me. So, I introduced in yesterday's class to you about equations, variables, constants, parameters. What are the different types of equations we have? Okay, so we spoke about different types of equations, and we also discuss some examples with respect to them. So today I'll be discussing about sets. Okay, so let me share the white. So can you see the white board?
Yes, sir.
So by now many of you might have heard about sets. So set of uh, goods, then set of books, set of pens, okay, set of clothes, etc., etc. So what does set actually mean? Set by definition is nothing but a collection of distinct objects. So set is nothing but a collection of distinct objects. So what can be those sets? So they can be set of natural numbers, that is n equal to 1, 2, and so on. So whenever we are writing a set, we write the objects, collection of the objects or the distinct objects within braces. Okay, and we define that set by a particular alphabet. That is, n is a set of natural numbers. Then we can have set of integers. So it is from negative infinity, that is -3, -2, -1, 0, 1, 2, 3, and so on. Okay. So then you can have set of vowels. What is a set of vowels? A, E, I, O, U. So whenever you are writing the elements of a set or the distinct objects of a set, you separate them by commas. Okay. So we have now a fair idea about what set is to begin with. Now set can be elements of a set or distinct objects of a set. Elements or distinct objects of a set can be enumerated. That means they can be written in details as shown above, or described, rather than writing in details all the elements of the set. So let us take this example. S is equal to 4. So we are writing this. So we are now writing this set by enumeration. So we are enumerating all the elements of the set. But when we speak about, let's say, a set that may contain infinite number of elements, it is not possible to enumerate all the elements of this set. So let's say we are considering a set of positive integers. So there are infinite number of positive integers, so we cannot enumerate all elements of the positive integers. So what do we do in that situation? We write something like this: x is a positive integer. So what do you mean? We mean that X is an element of a set, element of the set P, and X is a positive integer. So X is nothing but general representation of the elements of a set. Then this bar, this vertical bar is doing what? This vertical bar is nothing but separating this general representation of the elements of a set from its description. So on the right hand side of the bar, we have the description about the elements of the set or the members of the set. On the left hand side, we are representing generic, we are making a generic representation of the elements of a set. Now, set can have finite or infinite number of elements. Okay. So if you look at this example P, set P, where P is equal to X and X is a positive integer, so it has got infinite number of elements. Okay. But if you look at the set S, how many elements are there? Just 3 elements, 2, 3, 4. So this set S has got finite number of elements. Fine. Next, there is one more description that also has to do with the countability of the elements of a set. So let us consider these sets 2, 3, 4, p equal to x, such that x is a positive integer. Okay. Then we have got x equal to x, such that x is a real number and x is greater than 2 but less than 5. Okay, fine. So in the first case, you have got finite number of elements, whereas in the second two sets, that is set P and set X, you have got infinite number of elements. So in set P, what is happening? X is a positive integer. Okay. In set X, what is happening? X is a real number and X lies between 2 and 5. So in the first case, that is in case of set S, S is finite. It's a finite set because it contains finite number of elements, and countable because you can count all the elements of this set. Second set P, it has got infinite number of elements, so set P is infinite and countable because you can count the positive integers. Third set X, X is infinite because it has got infinite number of elements and uncountable because the real numbers that are associated, the real numbers that are between 2 and 5, the counting of such numbers, the real numbers that are between 2 and 5, they cannot always be associated with natural numbers like 1, 2, 3, 4, and so on. And hence, the number of elements, which is already infinite, that can lie between 2 and 5 in this example for set X are uncountable. So you cannot finish them by counting. Fine. Now, what can be relationship between two sets, two or more sets, but I'm just giving example with relationship between two sets. So let us consider two sets, S1, 2, 3, 4, S2, 2, 3, 4. So this is type 1 relationship. So here we can see all the elements of set 1, S1, and set 2, that is S2 are equal. So 2, 3, 4 are the elements in set S1, and 2, 3, 4 again are the elements in set S2. So we can say what? That is S1 and S2 are equal, or S1 is equal to S2. Type 2, S3 equal to 2, 3, S4 equal to 2, 3, 4, 5, 6. So what is now the relationship between S3 and S4? So we can see all elements of S3 are contained in S4. So in that situation, what do we write? We write that S3 is a subset of S4, or we can write alternatively as S4 contains S3. So symbolically we can write this as what? S3 is a subset of S4, or alternatively as S4 contains S3. Okay. So third type of relationship. So before we get to the third type of relationship, let us consider one more example. So S 2, 3, and 4. So here set S is a subset of itself, because it is containing its own element, so it is a subset of itself. Fine. So in the previous example, when S3 is contained in S4, that is S4 contains elements that are not in S3, then in such situation S3 is termed as a proper subset of S4. Okay. Now, in this example where S is a subset of itself, we cannot say that S is a proper subset of itself. Okay. Now, carrying this subset discussion further, let's say if a set has got n elements, contains n elements, then the possible number of subsets is given by 2 to the power n. Example, is 5. 3, 6, 9. So what are the number of elements? N equal to 3. So what are the possible number of subsets? 2 to the power 3 equal to 8. Now we'll find out what are the 8 possible subsets. So the first subset is this set itself. So S1, 3, 6, 9. S2, 3, 6. S3, 3, 9. S4, 6, 9. S S5, 3. S6, 6. S7, 9. S8, we write something this as 5, which is nothing but known as a null set. Now I will tell what is a null set. Phi or null set is a set that contains no elements. Okay. Now the question is this: why phi or a null set is a subset of this set S5? So let's say if null set contained an element that is not in S5, then we cannot say just a minute. So if null set contain an element, we can so if null set contain an element that is not in that is not in S5. Okay, so that is not in S5, then phi will not be a subset of S5. Okay, but since phi or null set does not contain any element, we cannot say that phi is not a subset of S5. Hence, phi is always considered a subset of S5. So in case of any set, now there is a general result. So in case of any set S containing any number of elements. So in case of any set S containing any number of elements, it will be, sorry, it is always the case that S and phi, that is null set, will be subsets of set S. Okay. No matter what are the number of elements contained in a set S, S itself and null set will always be subsets of set S. Okay. Let us consider a set 2, 3, 4. Okay. So here we see that that 2 belongs to S. So we represent this as what? We represent this as 2 using this Greek sign and epsilon. S, 2 belongs to S. Now 5. Do you find any element in element 5 in set S? No. 5 does not belong to S. So what? How we'll write this as 5? So we'll write. So we will put the epsilon sign and then we'll cross it, which means that it does not belong to. So 5 does not belong to set S. Okay. So we have already discussed two relationships, two types of relationships between two sets. That is, the two sets can be equal, okay, or a set can be a proper set of the other given set. Now, what can be third type of relationship? Type 3. So A6, 2, 3, 4, A7, 5, 6, 7. So let us see with respect to type 1 relationship. Are set S6 and S7 equal? Yes or no? Are set S6 and S7 equal? Students?
Yes, sir.
Are they equal? How? How they are equal? What? No. When can two sets be equal? Tell me. Uttama. When can two sets be equal? When can two sets be equal? Now tell me, when can two sets be equal? Hmm? Kanishta, tell me. When can two sets be equal? So two sets can be equal. So here I have already shown S1 and S2. Two sets can be equal when they contain the same elements. So are they containing same elements S6 and S7? Are they containing the same elements S6 and S7?
No, sir.
Then they are not equal. Fine. Now next, S6 is S6 a subset of S7?
No,
Is
sir.
huh? Is
No,
it?
sir.
Okay.
No, sir.
Is S7 a subset of S6?
No, sir.
Okay. That means what? In this case, when none of the elements are common, so you see, none of the elements of set S6, 2, 3, 4 are common with the elements of S7, 5, 6, 7. So in this case, we say that S, we say that S6 and S7 are disjoint. Okay, so they are disjoint. So this is third type of relationship which you can have when none of the elements, when not a single element are common among the between these two sets, then S6 and S7 are disjoint. Type 4, S8, 2, 3, 4, S9, 3, 4, 5, 6. So in this case, S8 and S9, first of all, S8 has got 3 elements, S9 has got 4 elements. So anyway, these two sets are not equal. So type 1 relationship rejected. Type 2 relationship, S8 contains at least one element, that is 4, which is not contained in S9. Sorry, I'm sorry. S8 contains one element 2, which is not contained in S9. S8 contains at least one element 2, which is not contained in S9. Look here. So that means S8 is not a subset of S9. Fine. Now, S9 contains at least two elements, 5 and 6, that are not contained in S8. So it contains two elements, 5 and 6, that are not contained in S8. So S9 is also not a subset of S8. So type 2 relationship also rejected. Type 3 relationship. S8 and S9 contains two. S8 and S9 contains two elements that are common, that is 3 and 4. So that means there are at least two elements between set S, between sets, so they are not disjoint. So that means in such a case, in such a type of relationship, we cannot say so S8 and S9 are neither equal nor subset of each other, and neither are they disjoint. Okay, so that means consider two sets, then there can be 4 types of relationships. Type 1, when both the sets contain the same elements and the same number of elements, then both the sets are equal. Type 2, there are two sets. So one set contains all the elements of the other set, and over and above contains some elements which are not contained in the other set. Then the other set is a subset of the given set in question. Okay. Type 3, when both the sets contain no elements in common to each other. When both the sets contain no elements common to each other, then both the sets are disjoint. Type 4, when both the elements, when both the sets contain some elements that are common to each other, that means they are not disjoint, but they also contain certain elements which are not found in the other set, that is they are neither equal nor they are subset of each other. Okay, so these are the 4 types of relationships which we can come across. Next, operations on sets. So when you're conducting operations on sets, so there can be three types of operations basically: union, intersection, and complement. So what is union? So let us consider A and B are two given sets. Okay, A and B are two given sets. Now when we say A union B, we mean this. We use this symbol A union of B. So this A union of B is itself a set. Understand this thing. A and B, they are already two given sets. So when we write A union B and represent it symbolically as follows. So A union B itself is a given set. So what does this mean? So general representation of the elements of this set A union B is X. And how do we describe X? We say that X belongs to A or X belongs to B. Okay. So let us take an example. Okay. So how will we write A union B? So we already know the definition. X belongs to A or X belongs to B. So X belongs to A. What belongs to A? 2, 3, 4. Or X belongs to B. So 2 belongs to B, but 2 also belongs to A. That means it either belongs to A or it belongs to B. 3, it belongs to A. Done. 4, it also belongs to B. So it also belongs to A. So we already mentioned. So we'll have to consider now those elements that are not in A but are in B. So we have already written X belongs to A or X belongs to B. That means it has to be in either of these two sets. So 6, 7. Okay. So now let us work out some practice. Let us do some practice. C equal to A, E, I, O, U. D equal to I, U, C, D, E. So what is C union D? Tell me. Students, work this out and tell me what is, students, work this out and tell me what is C union D. Work this out and tell me what is C union D. So what are the elements of this set C union D? Ezra?
Sir, I've written in the chat box.
Oh, you have written in the checkbox. Let me see.
Yeah.
Checkbox. Okay. So you write it in the chat box. Tell me.
Sir, the elements are A, E, I, O, U, C, and D.
Okay. Just a minute. Let us write A, E, I, O, U. Then
C and D.
very good. Fine.
Yes, sir.
That means this set, that is C union D, contains those elements that are either in set A or in set C union D contains those elements that are either in set C or in set D. Okay. Any doubt? Anyone? Any doubt? Anyone? Please tell me.
No, sir.
Okay, fine. So now we go to the next step, that is intersection. So intersection. So when we write, let's say, when we mean this, that is A intersection B. We represent this by symbol A intersection B. So this is itself a set, intersection B. What does this mean? X such that X belongs to A and X belongs to B. That means X should be such an element of this set A intersection B. That means should be such an element of this intersection set that is A intersection B. That is, it should be common to both A and B. So X should belong to both A and B. So X should be common to both A and B. So all the elements of this set, that is A intersection B, should be common to both A and B. So now let us work out an example. A 2, 3, 4, 5. B 5, 3, 6, 7. So now A intersection B, this set should contain only those elements which are common to both A and B. So which elements are common to both A and B? 3, okay, and 5. So let us work one more example. C equal to 11, 12, 15, 17. D equal to 9, 10, 11, 13. So find out C intersection D. Find out C intersection D and tell me what are the elements.
Sir, the answer is
Huh?
11.
11. Okay. So let us work one more example. E equal to A, E, I, O, U. F equal to B, C, D, F, G. So find E intersection F and tell me.
So can we write it as null set? Null set.
Yes. There are no elements that are common to a set A and B, so it is a null set. Very good. Clear?
Yes, sir.
Any doubt?
No, sir.
Okay, that's great. So, lastly, there is one more operation that we carry between two sets, that is complement of a set. So before we go for a complement of a set, we have to define a universal set. So universal set is a set that contains all the elements. So this is the definition. Okay. Next, then what does a complement of a set means? Complement of a set means those elements that are not contained in the set, contained in the set, but they are contained in the universal set. Okay. So let us now define an universal set for an example. For example, U equal to 1, 2, 3, 4, 5, 6, 7. Okay. And A is one set 4, 5, 6. So when we write complement of set A, we denote this by symbol A with a superscript of C. So A superscript of C denotes the complement of a set A. So this is itself another set. So it means what? It means those elements, complement of set A means those elements, set of those elements that are not contained in set A. Okay, but they're contained in the universal set. Okay, so we know what are the elements of set A. 4, 5, 6. What are the elements of the universal set? 1, 2, 3, 4, 5, 6, 7. Okay. So what should be complement of set A, that is AC? Those set of those elements which are not contained in set A, but they are contained in the universal set. So what are those elements? They are 1, 2, 3, 4, 5, 6 are there, and 7. Okay. So working out an example, U equal to 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Okay. Then A, not A, B, 23, 25, 29. So what is B complement or complement of set B? Find it out. B complement or complement of set B. And tell me what are the elements of this set, that is B complement or complement of set B.
So the complements of set B are 21, 22, 24, 26, 27, 28, and 30.
Okay, very good. So B complement is 21, 22, 24, 26, 27, 28, 30. Clear?
Yes, sir.
Okay, now we will show diagrammatically using Venn diagrams all these three operations on sets. Okay, Venn diagrams. Fine. Now let's say we are representing So we'll represent set with circles. Okay, so this is a given set. This is also a given set, A and B. And we represent a universal set by a rectangle or a square. Okay, so this is U, typically, which is the universal set. Redraw it. Okay. Now, when we say union, two sets, that is A union B. So we will represent this as follows. This is B, this is A. So this entire shaded area will represent A union B. Okay. That means it is contained either in set A or in set B. Now next, intersection. A intersection B. Again we draw. So A intersection B means what? The elements which are common to both set A and set B. So this is nothing but the intersection between these two sets. That is the area or the elements that are common to both set A and set B. So the shaded area. Okay. And the last one, which is complement. So first we draw the universal set. So this is my universal set. Now there I draw a set which is A. Now look very carefully. A are contained in the universal set U. Okay. All the elements of set A are contained in the universal set U, but not the other way around. So there are certain elements of set U which are not contained in set A. So this shaded area so this shaded area is representing what? This shaded area is representing A complement C or complement of set C. A complement or complement of set A or written as A with a superscript C. Okay. So the shaded area is representing complement of A or A complement. That means those set of those elements that are not contained in set A but they are contained in set U or the universal set. Now, there are, let's say let us now consider three sets, set A, set B, and set C. So three sets are there. Now, like arithmetical laws, there are also certain laws of set operations. So what are those three laws of set operations? Commutative, associative, and distributive. Okay, fine. So what does commutative law say? Commutative law says commutative law for two sets. Commutative law for two sets A and B. So whenever we write A union B, it also means B union A. Similarly, whenever we write A intersection B, it also means B intersection A. So let us take an example. A equal to 2, 3, 4. B equal to 4, 5, 6. So in this case, if you see, what we will write A union B, elements that are either in set A or in set B. So they are what? 2, 3, 4, 5, 6. Similarly, B union A, what are the elements? The elements that are either in set B or in set A. So what we will write? 4, 5, 6, 3, 2. So the elements in set A union B are same as the elements in set B union A. So we can write this clearly. A union B equal to B union A. Now next, A intersection B, elements that are common to both A and B. So what is elements that are common to both A and B? Just 4. Now B intersection A, elements that are common to both B and A. So what is that? Again 4. So we can write it. So this implies what? A intersection B equal to B intersection A. Okay. Now next we come to associative. Associative law for three sets A, B, and C. So what is associative law? A union B union C. So this we can write clearly as A union B union C. So if there are, okay, just a minute. I wrote the same thing. So here, associative law for three sets A, for three sets A, B, and C. So A union B union C. So A union B. So it is the first. So this is one set. So we have got three sets A, B, and C. So we are forming the union of two sets A union B, which is itself a set. Now we are now making union of this set A union B with that of set C. So this should be equal to what? This should be equal to this, that is A union with the set which is found by union of set B and set C. So let us now see an example. A equal to 2, 3, 4, B equal to 4, 5, 6, C equal to 4, 7, 8. Okay. Now we'll have to, this was page 9. So next we have to go to page 10. Okay. So first let us find A union B. So what is this A union B? Elements that belong to either set or set B. So there are 2, 3, 4, 5, 6. Okay. Now we'll have to find union of this A union B with that of A union C. That means the elements that are either in set A union B or in set C, which is 2, 3, 4, 5, 6, 7, 8. Now we look the other way. A is already given, so now we have to find B union C. Elements that belong to either set A or set elements that belong to either set B or set C. So which is 4, 5, 6, 7, 8. Now we'll have to find A union with the B union C set, which is nothing but 2, 3, 4, 5, 6, 7, 8. So this means what? So it shows very clearly that A union B, with that you make a union of C. Then A union, with that you make a union of B union C. So this implies that. So this is one part of the associative law. What is the second part of the associative law? So this is part 1, part A of the associative law. So there are two associative laws for three sets A and B. Now this is part A. What is part B? Part B says A intersection B intersection C should be equal to A intersection with sorry, A intersection B with that of B intersection C. Okay. So here we can find it out. A intersection B is equal to how much? A is equal to what? A intersection B. So 2, 3, 4, 4, 5, 6. So we have got 4 as the common. Next, what we do? A intersection B intersection C. So A intersection B, we already have 4. What we have got in C, 4, 7, 8. That means it is 4. Next, we have to make B intersection C. So B intersection C is how much? Is what? B intersection C, 4, 5, 6. B, C is 4, 7, 8. So again, we get 4. Next, we have to make A intersection with that of B intersection C. So A has got what elements? 2, 3, 4. And B has got what? B intersection C has got what element? 4. So common element 4. So this implies what? A intersection B with that intersection C, then A intersection B intersection C. Okay. So this forms your associative law or distributive laws. For three sets A, B, and C. So part A. So then again there are two laws. So what is the part A law? Part A law says A union B intersection C is equal to A union B intersection A union C. So again, let us look at the examples. 2, 3, 4. B equal to 4, 5, 6. C equal to 4, 7, 8. So B intersection C is how much? So not how much. We should not be using the term. We should not be using the term how much in case of set operations. We should say what are the elements. B intersection C. So the common element is 4. Okay. So now you have to make A union with that of B intersection C. So what do we get? 2, 3, 4. Okay. So now this is the first part. Second part, let us see what is A union B. This is nothing but 2, 3, 4, 5, 6. Similarly, A union C. What is this? This is nothing but 2, 3, 4, 7, 8. Now, A union B. So this is one set. So I'm intersecting that with A union C, the other set. So what are the elements common to both A union B and A union C? 2, 3, 4. So this implies what? This implies A union B intersection C is equal to A union B intersection A union C. So this is part A of distributive law. Part B will be done very soon. Just bear with me for some more minutes. A intersection B union C. So this will be written as A intersection B union A intersection C. So let us now see first. So what is B union C? 4, 5, 6, 7, 8. So what is A intersection B union C? So A was what? A was 2, 3, 4. So here we get what? Here we get 4. Now let us look at the other part. A intersection B. So B was what? B was 4, 5, C. So intersection B. Common element is what? 4. A intersection C. C was what? 4, 7, 8. So what is the common element? 4. So A intersection B union A intersection C is what? 4. So this implies what? A intersection B union C is equal to A intersection B union A intersection C. Okay. So this is what we have for today's discussion. Okay. And for this, I am following chapter 2 of Chiang, 4th edition. Okay. So Chiang, we have got this book. I think Jugal sir might have introduced to this book. Fundamental Methods of Mathematical Economics, 4th edition, McGraw-Hill. Okay. Fundamental Methods of Mathematical Economics, 4th edition, Alpha C. Chiang, Kevin Wainwright. So from here, I am following chapter 2. Okay. So you can go from page for chapter 2. For the last 2 classes that I have followed for chapter 2, you can follow from page 18 till page 27. Okay, fine. And try to work out the exercises that are given at the end of each section between page 18 and page 27. So there are three sets. There is only one set of exercise, that is exercise 2.3, which is at the end of page 27. Try to work out the problems. So we'll discuss problems in the next class. Okay. So any question? Any question, anyone? Okay. So thank you and have a nice evening.
Thank you, sir.
Okay.